Welcome to another episode of the Distributed Data Show, brought to you by DataStax Academy, where we bring you the latest news and interview technical experts to help you succeed at building large-scale distributed systems.
Hello and welcome to another episode of the Distributed Data Show. I'm David Galore, a technical evangelist here at DataStax, and this is Dr. Denise Gosnell. I just had to do that because doctor is awesome. Yeah, hi.
Hi. If I weren't awake, I am now.
Oh, good. I'm glad. I'm glad that I could help you be awake for this particular show. So, in a previous show, we talked about what is and what isn't a graph problem, and we left with three classifications. Can you kind of talk about what those are?
Yeah, it was a good conversation, and it's a part of what I'm doing here at Day-to-Day Texas to continue to look at problems and break them down into whether or not they are a graph problem, and if we know we have graph data, whether or not it belongs as like a graph analytics or a graph database problem.
Okay.
So that's part of what I'm talking about here, and that was where we kind of left off one of our last data shows. And so I kind of wanted to pick up on that for our show today.
Okay. So today it sounds like we're going to talk about some weird ways to apply some graph analytics
Yeah.
problems. Like you just said, I'm totally repeating back what you just said. And so it sounds like you've got some graph invariants that you want to talk about. What are they?
Yeah, so across those three buckets, focusing on graph algorithms just for fun because graphs are really cool, and
yeah, they are.
Who doesn't love graph algorithms?
Totally cool.
At least in my world. So there's some very interesting and weird ways to apply a chromatic number, augmenting paths, and then locating domination or total domination.
Total domination.
No, for real.
We're going to talk about that.
Like these are real graph invariants that you would study in graph theory, and
Okay.
there's tons of papers that my advisor writes on these things.
Huh?
And so I kind of want to talk about today interesting ways to apply those three things to solve different problems.
Okay. All right. Cool. So you mentioned chromatic number.
Yeah.
Right.
Yeah.
What is chromatic number? Can you
So the best part about graph theory is that everything is very visual. So I'm going to make you think about this in your head, okay?
Ooh.
All right, so just pick a small graph, maybe 5 vertices or so.
Okay.
And just put some edges between those vertices.
Okay, I'm doing it, totally.
So the chromatic number is the way that you would put color on the vertices.
Okay.
So that if they're adjacent or if there's an edge between them, they're not the same color.
Yeah, okay.
So that's all a chromatic number is.
So it's like a graph coloring book.
Actually, I'm glad you say graph coloring book, because when I started graph theory, the very first thing I thought about was those coloring books you did when you were little.
Yeah.
And it was like 1, 2, 3, 4, and you like draw.
And you know what? Honestly, that's what came to mind when you. Okay. It really did. Now you see where my mind is.
It's close. It's close.
Okay.
But the chromatic number of a graph is, if you were to take any graph of vertices and edges, the minimum number of colors needed.
Okay.
So that no two adjacent vertices had the same color.
Okay.
So that's what a chromatic number is.
Okay.
And you can, just get your pen and paper out and you can start playing with it.
Yeah.
You can also think about like the map of the world, and the countries are vertices.
Okay.
And if you're adjacent to a country, like you share a border, there's an edge between them.
Right.
And then you can now see how people color world maps, because if you look at them, no countries are the same color.
Okay.
It's actually part of the very famous 4 coloring problem. Another side note tangent. But that's actually how they determine how to color a map out in the real world.
Oh, that's cool.
Yeah.
Okay. Okay. So what kind of, is there a particular use case or something that you might use, apply this particular invariant to?
So beyond the coloring of map, which is a pretty obvious one when you study the chromatic number, where you apply it, there's a really weird way to apply it.
Okay.
And I've seen this done before for how you would say schedule different operations in a hospital.
Okay.
And so the weird application of a chromatic number or graph coloring is how you would do a scheduling problem. And what you would do, and I'm talking about this today at DataStax.
Oh, awesome.
You would set up your vertices to be the things that you need scheduled. So you've got this operation needs to be scheduled.
Okay.
And so you create all these vertices according to what needs to be scheduled. And then you start putting edges in your graph according to different conflicts.
Okay.
So what we're building a conflict graph.
That's cool.
So if for some reason a certain operation needs the same doctor,
okay.
that operation can't happen at the same time.
Right.
So you'd put an edge between those two vertices.
Okay.
Or maybe these two operations require the same equipment that's very limited.
Okay.
You'd put an edge between those two vertices because they need the same room or equipment. They can't happen at the same time.
Okay.
So you'd have to think about your use case, think about the conflicts as to why your operations can't happen at the same time, and you'd build a conflict graph.
Okay.
All right, so now we have this conflict graph, and I told you it's related to graph coloring, so where in the heck is that going to come in? What you would do from there, you would take this graph, and you would go through and you would color it. You could just do a breadth first search, start at one vertex, assign it a color, go to its neighbors, assign a different color, and you'd go throughout your graph and determine a coloring of these vertices. The operations that can happen at the same time are the operations that are the same color, because there's no conflict between them.
Oh, that's neat.
Yeah.
That's totally cool.
Yeah, so you'd go through and you'd find all of the orange vertices, and if this was an operations scheduling system, all of those operations could happen at the same time within the hospital because there's no conflict between doctors, rooms, anything like that.
Oh, okay,
So
very cool.
That's an interesting way to apply a chromatic number.
I didn't, that was neat.
Yeah.
That's very cool.
Yeah.
Okay, so it sounds like that's something you could probably apply to like scheduling day-to-day
Yeah.
or scheduling other conferences
Yeah,
or something like that.
I've been joking with Lynn Bender actually
Yeah.
and some of the guys from Expero downstairs how we really just need to help them out and we just need to put this up and go ahead and get a graph frame running so that we can help them with scheduling this event because it turns out to be difficult for them every year. So
I think that's kind of a fun project that
I know.
I think we should just do
if
that.
we're at a graph conference, why are we not scheduling it with the chromatic number of
I
the
like
graph?
that. Yeah, that's awesome.
I'm just saying.
That's cool. Okay. So then you, yeah, I like that. So then I think the second one you talked about was augmenting paths, the second invariant. So what's that? What's that?
Yeah, so an augmenting path it's a pretty technical component that comes out of a single source shortest path algorithm.
Okay.
So what happens is you have a source and a target, and you apply Dijkstra's or you apply one of your other path finding algorithms to find a way to get from your starting point to your end.
Okay.
When you're doing that, you would add in an extra data structure to calculate an augmenting path as you're going through this path finding algorithm. The augmenting path is the way that you would apply a matching within a bipartite graph.
Okay.
So an augmenting path is just it's a byproduct, say, of a Dijkstra's algorithm.
Okay.
And it's not something you normally track when you do Dijkstra's. This is something you'd have to add on to it. But there's a really cool way to use these augmenting paths to match things.
Okay.
So what you'd be matching is you'd be matching something that would be constructed in a bipartite graph.
Okay.
A bipartite graph is a graph where you have two sets of vertices or more, like tripartite, etc.
Okay.
But we'll just start with two. So you have two sets of vertices, and a bipartite graph is a graph where there's not edges between the vertex sets.
Okay.
So let's think students and class schedules, right?
Okay, right.
So all of our vertices are students, and then we have, that's one set, and another set of vertices are our classes.
Okay.
And in this system, the students say, this is my first preference of a class, my second preference of a class, and all the students give their preferences.
Okay.
It's bipartite.
Okay.
Because we're not putting edges between the students and we're not putting edges between the classes.
Right.
So that's the bipartite graph part. So a way to find an augmenting path here is that you would want to find a matching that's going to use these student preferences to match them to a class schedule and do it the best you can, right?
Okay.
Like you don't just want to assign everyone the class they didn't pick or the class of their least preference. Like that's just mean.
So is this something that could be used to, say, help the student kind of get their class schedule, based off of the preferences essentially that they have chosen?
Right.
Okay.
Right. And
okay,
it's a way to apply a unique way to optimize that for maybe weighted preferences.
Okay.
And so I mentioned Dijkstra's and I've mentioned augmenting paths. And all I've really told you, though, is that we have a bipartite graph and some selections that students have made about classes. So where do these two things come together?
Right.
You would take your bipartite graph, you would add a source and a sink. So all students would be connected to the source, the starting vertex.
Okay.
So you'd have a start vertex that connects to all your students, and we'd call that the source.
Okay.
And then you'd have a sink. You would connect all of the classes to the sink vertex at the end.
Okay.
And now what we want to do is we want to do a path algorithm between the source and the sink.
Ah.
You would do Dijkstra's from the start to the end. You'd go through your bipartite graph with the directed edges of students to classes. And the resulting augmenting path that you would derive from doing that would be the best matching of students to classes.
That's okay. See, this,
so
by
that's
the way,
where that comes together.
This is why when I introduce you, I'm like, Dr. Denise, you can feel the doctor. You can.
Well, I'm very blessed to have found this amazing passion that I have, and that it's relevant in technology right now. And I could sit here and talk about different ways to use graph invariants like all day.
Yeah, I'm gonna honestly after we do this, I'm totally picking your brain because I want to know more about this. I mean, honestly, there seems like there are some really neat problems that we could solve with all sorts of our tools and stuff, and I'm wondering how we can bring that in what we do. So you've kind of piqued my interest here.
Well, we're going to start. Apparently, we're going to start a side project where we schedule conferences.
Oh, it sounds like it. I think we should just do that.
And then we can even make everyone's schedule for them by having them pick their talks, and then we can match the talks to the attendees.
Rad.
Yeah.
I think that's fun.
We've
All
got
right.
some projects.
Yeah, all right. I'm down. I'm down. Now you talked about the last one there in your summary in the beginning, which is, I'll have to admit, it's my favorite one. It's total domination.
Yes.
Like, tell me about total domination.
Yeah,
It's
so,
just, how do you not say that and not say it that way?
I mean, maybe because I was, I had the
Maybe it's
honor
me.
of like working with the professor, Dr. Teresa Haynes.
Yeah, okay.
Who is like the main professor who was my master's advisor, and I admire her to the end of the earth.
Yeah.
She primarily works with studying domination, total domination, locating domination in graph structures, and so I had the privilege of working with her. And she also works with Hetnimi and Henning, and they're all connected with Erdős. So I have a short Erdős number because I got to work with her. So it's pretty cool. But because I had the privilege of really diving in and understanding the full mathematical implications of domination number, do I just really appreciate it and not see it for what other things might be contrived from that type of name.
Okay.
But what in the heck is a domination number
I was about
in
to
graph?
ask you, like, what is
like,
this?
why are we dominating graphs? So in that graph you pictured earlier, what we colored. Okay, bring that graph back up.
It's back.
But it's back. All right. So instead of having colors in the vertices, erase all your colors.
Okay.
And now what we want to do is we want to pick the smallest set of vertices so that every vertex in the graph either is in that set or touches somebody in that set.
Okay.
So let's start with a simple graph, a star graph.
Okay.
You have one vertex, and then every vertex kind of branches off that star.
Right.
A domination set for that graph is just the center vertex, because everything either is in the set or touches somebody in that set.
Okay.
And so now think of a path, like you walk one vertex to another, to another, to another. Basically, every other vertex has to be in the dominating set because you either have to touch somebody in the set or be in the set yourself.
Right. Okay.
So there's an entire field of mathematics that studies the way to apply this number.
Okay.
And that was the one I wanted to talk with you about today.
Yeah. I was going to ask you, like, what's the application? Right?
Yeah, the application of this is actually for safety and security, where you would look at how you would use a locating dominating set to uniquely identify any vertex in the graph.
Okay.
Okay, well, why does that matter? I mean, we're in a really big building right now.
Yeah.
And you can kind of picture putting in certain alarms in this room, the room next to us, the hallway.
Yeah.
You can imagine that if there's a certain set of alarms going off, you would want some central system to know immediately where the problem is in the building.
Right.
And that's what a locating dominating set does.
Okay.
You put vertices in the locating dominating set, and then you would pull two of them. And then that would uniquely identify either that set or which other vertex in the graph would be relevant according to which ones are in the dominating set. And the application is or the locating dominating set. And the application really is placing fire alarms in a building. So if this hallway is going off, but also this hallway, it's probably the adjacent room where the issue is.
Oh, that's neat.
If it's just this hallway that's going off and this one isn't going off as well, that means it's probably just the hallway where the problem is.
Okay.
So it just depends on how you place your alarms and using the set of alarms to determine where your issues are.
I kind of want to set this at home, like set
Yeah.
this all up at home and go off my fire alarms. And,
some motion detectors is a way to determine like where the problem is.
Or smoke detectors and
smoke.
I said fire alarms, I meant smoke detectors, but whatever.
It works.
I think we understood.
We did. And I mean, people have been doing this for years, right? Like people have been intelligently putting fire alarms in their house for years.
Yeah.
Who knew that there was an entire mathematical field of study to like optimally place these fire alarms so that you don't put too many, but you don't put enough, Clearly not putting enough, it could be a big problem. But so there's an entire field of math, and I've had the privilege of working with Dr. Haynes, and we have some papers out there that kind of talk about different properties and how you'd place these things. So.
Okay.
Yeah.
Oh, that's great. Yeah, no, all the things that you've kind of expounded on today, like, these are all problems that, at least to me, I'm a little new to all of those subjects, right? And I did not know that these were particular things that were being addressed, right? And I'm totally interested. This is like piqued my curiosity in all this. So.
We've all been training, all of us, to really have graph theoretic minds since we were kids with those coloring books of going one. I mean, graph theory has always been all around us, and
I kind of like that. We need to make a video on graph coloring book and kind of use that as a way to explain.
During our side project that we're scheduling conferences.
Yeah, we're scheduling all the side projects.
We're going to make graph books as well.
Okay,
I like that.
Works. I like that idea. Okay.
I think we're starting to sign ourselves up for a lot of projects.
I think so. Yeah, maybe we should stop. Yeah. All right. So as we, I just want to kind of wrap things up and all that kind of deal. And I know the intent is to do a couple more of these and
Yeah.
kind of talk about some more problems. I think you were wanting to push in some data modeling and
Yeah.
stress testing supernodes. Like,
Yeah.
can you give me just a little quick summary on what that's going to be so we can?
Yeah, in the spirit of signing myself up for more things.
Yeah, sign
right?
more stuff up.
Yeah,
That's right.
When we kind of concluded the first what is a graph problem, what's not a graph problem conversation, we left ourselves these general topics: not a graph, graph analytics, graph databases. And since I've been working with some really cool graph projects that we have going on here at DataStax, I have found that the biggest issue that people kind of get a little concerned about are supernodes, and how do we either model around them or traverse through them.
Yeah.
So we're going to be doing some stress tests coming up, and I think it might be fun to come back and talk to you guys about the different ways I would model around a supernode, and then potential ways to even do paths through supernodes.
Yeah. Okay. Awesome. No, that sounds great. So I think we're gonna sign off there. And again, thank you for watching another episode of the Distributed Data Show. See ya.
Thank you for joining us again for the Distributed Data Show. We love your feedback, so go to the Distributed Data Show page on DataStax Academy and tell us what you think. You can also find us on the DataStax Academy YouTube channel, or find our podcast on iTunes, Google Play, or wherever you get great podcasts. While you're there, make sure and subscribe so you don't miss a single episode.